Welcome back to our next episode of Econ 461 Game Theory. Right now we're looking at the grenade game. It illustrates the idea of non-credible threats. So this example is not one that I invented myself. It came from a University of Washington professor. He imagines the following scenario. So a stranger comes up to you and says, "I have a grenade, and you better give me $100. We're going to pull the pin on this grenade and kill us both." So you have two choices here. You can pay or you can not pay. If you choose pay, the game is going to end. If you do not pay, then the other player, which we will call Grenade Guy or GG, has a choice of either playing use grenade or not use the grenade. So it's a sequential game. You guys are taking turns. You choose pay or not pay, and after that is observed, then Grenade Guy can choose what to do with the grenade. We'll try the game tree format first and find the rollback or subgame per Nash Equilibrium. Then we'll look at it as a simultaneous move game and find the Nash Equilibrium and see if there are any issues with non-credible threats. So here's the game tree. Showing your options are either pay or don't pay. So if you pay, you're going to lose $100. I'll call it minus 100 for you. Grenade Guy's paths here, shown in blue, are going to be plus 100. Now if you play don't pay, now GG, that is Grenade Guy, has their two options. If they don't use the grenade, then nothing changes. I'll model that as a path of 0 for both of you guys. Now if Grenade Guy does use the grenade, that kills both of you. I'll model that as paths of minus 100,000. So now go ahead and pause the video here for a moment and find the rollback equilibrium. When you're done, press continue. Alright, I presume you found the rollback equilibrium. So Grenade Guy over here is going to play don't use. It's better to play don't use and get 0 than it is to play use and get this massively negative payoff. So if Grenade Guy is going to play don't use, then you're going to play don't pay, because don't pay is going to get you a payoff of 0, and that is better than losing $100 and getting minus 100. So it's going to be unique rollback or subgame perfect Nash Equilibrium, which is don't pay, don't use. So now we'll translate the game into a simultaneous move form. So we're at the table, and let's make you the row player, and Grenade Guy GG is going to be the column player. So to give you guys some practice, I'll pause here for a moment and let you guys try to figure that out on your own, and then when you're done, press continue. Alright, so presumably you did it. So here's what you should have come up with. So if you play pay, the game just ends. So your path is minus 100, Grenade Guy gets plus 100. Remember, as always, row player's path comes first. So the game just ends if you play pay, then it's going to be the same payoff for both these cells here. They're both going to be minus 100 for you, plus 100 for Grenade Guy. If you play don't pay, then payoffs for don't use are going to be 0, 0. That's shown over here. And the payoffs for use are going to be minus 100,000 for both. So now go ahead and pause the video again, do your best response analysis, and find the Nash Equilibrium or Nash Equilibria. So go ahead and pause here, press continue when you're ready. Alright, so let's go talk about the Nash Equilibrium. So best response to use is going to be pay. You'd rather lose $100 than die. So that's your best response to use. Best response to don't use is to play don't pay, because that gets you 0, and that's better than losing $100. Now switch perspectives here. If your strategy is pay, Grenade Guy's best response is both of them. Remember, if you play pay, the game ends, Grenade gets $100, so that's it. So both those are best responses. If you're playing don't pay, then Grenade Guy's best response is don't use. He'd rather get 0 than get this massively negative payoff. So now look at where the underlines are, and we have two Nash Equilibria. We have the don't pay, don't use Nash Equilibrium, the one that's also a rollback or subgame perfect Nash Equilibrium. We also have this other Nash Equilibria, pay use, which was not subgame perfect. So for the second equilibrium, the non-subgame perfect one, there is an issue with a non-credible threat. Remember I said earlier, if there's a Nash equilibrium that's not subgame perfect, there's always a non-credible threat issue. So what's going on here is to make pay use an equilibrium, Grenade Guy's threatening, I'm going to use that grenade, and that's going to scare you into playing pay. So pay is best response to use. However, if you think about it, that threat to use the grenade is not actually credible. Grenade Guy would kill himself by doing that, and we're going to assume he doesn't like that. So you shouldn't believe Grenade Guy's threat to use the grenade. As a result, you're not going to play pay, you're going to switch to don't pay. So the threat to use the grenade is not credible. That's why that pay use Nash Equilibrium is not subgame perfect. Now I sense a possible objection here. If in real life someone did threaten you with a grenade, you would probably doubt their sanity, right? This person might not be trying to just get $100. They might actually be pretty crazy, and that might alter their payoffs. So this is the point where you hear some objections from a social science journalist who doesn't really understand economics. They say things like, economists assume people are rational, but in the real world people are crazy, so a lot of economic assumptions just don't make sense. That is not true. The way you use rational economics is not the same as the way rational is used in everyday English. So in economics in particular, in game theory, rationality means payoff maximizing. Someone who is certifiably insane can still be maximizing a payoff. There's maximizing payoffs that are radically different than what the rest of us are accustomed to. So here's how you can model the game. Where we have external uncertainty, in this case we don't know if he's sane or crazy, we model that as having a third player nature make a move at random. So with probability 30%, just to pick a number, he's sane. In that case, the payoffs are the same as we saw before. So in that case, if Grenade Guy is sane, Grenade Guy does not want to use the grenade because a sane person does not want to kill themselves. So payoffs are minus 100,000 for using the grenade. But if someone threatens you with a grenade, chances are they're probably not sane, they're probably crazy. So here's how I model crazy Grenade Guy's payoffs. Crazy Grenade Guy does like getting money, so that's why I threatened you in the first place, to try to extract $100 from you. So payoff is still plus 100 for using that. If Grenade Guy does not use the grenade, there's still no change if you don't pay, so this is still 0-0. The innovation we'll introduce here to model Grenade Guy's insanity is that maybe this crazy guy actually does like killing himself if he doesn't get paid. So I'll model his payoff as being positive 10 if you don't pay him, reflecting that his favorite choice is getting paid. If he doesn't get paid, he'd rather kill himself. It's crazy, but it can still be modeled as rational in the sense of being payoff maximizing. There is a way you can consistently order these payoffs for crazy Grenade Guy. So yes, game theory does still apply, even if people are crazy sometimes. So that's how you can model the game. So we'll do similar analysis as before. We'll look at what's the rollback equilibrium, and we'll also look at what is the Nash equilibrium. So to find Nash equilibria, we know how to do this from earlier. We know that we should be converting the game into a table. Each row or column in a table is going to be one of the player's strategies. So first you gotta list what are the possible strategies for each player. It's going to tell us how many rows and columns our table is going to have. So you have two strategies. You can either pay or you can not pay. Now remember here, you don't know which of these two nodes you're at. You don't know if Grenade Guy is sane or crazy. So you can't condition a response on Grenade Guy's sanity. You can't pick something like don't if sane and pay if crazy because you don't know if he's sane or crazy. You just play pay or don't pay, that's it. You have only two strategies. Now Grenade Guy does know which node he's at. I intentionally did not draw the information set around these two nodes. Grenade Guy's going to know if he's sane. Grenade Guy's also going to know if he's crazy. He's going to know which one reflects his true payoffs. So Grenade Guy is going to have four strategies because Grenade Guy knows where he is. Grenade Guy could play use at both these nodes. So use is a strategy. Don't use is also a strategy for Grenade Guy. Grenade Guy can also do something else. Grenade Guy could play I'll not use the grenade if I'm sane, but I will use it if I'm crazy. Alternatively, Grenade Guy could use the grenade if sane and don't use if crazy. That gives us a total of 4 strategies. So that means our table is going to have 4 rows or columns for Grenade Guy and 2 for you. Now, because of the uncertainty here, as we don't know which node we're at, you're going to have to take expected values in order to find your expected payoff. So here's how that is going to work. So first, here's the table. I made Grenade Guy the column player because I have more space with columns. I have 4 columns. And you're the row player with your 2 strategies, pay or don't pay. To make sure it all fits on one page, I abbreviated S for sane and C for crazy. So here's, I'm not going to use the grenade if I'm sane, but I will use it if I'm crazy. That's what this column represents. So now here's how I'm going to use expected values to fill in the table. We're going to start by picking the low-hanging fruit. We know that if you pay Grenade Guy, the game just ends. So if you pay Grenade Guy, then no matter whether Grenade Guy is sane or crazy, the payoff is going to be minus 100 plus 100. So you can fill in those 4 cells right away with those 4 values. So we're already halfway there. Now these next cells here are going to be a little bit trickier to deal with. That's because the payoffs in this case will depend upon whether Grenade Guy is sane or crazy. And there's going to be some randomness involved in that. So that's going to make our math more complicated, but still manageable. Alright, filling in our next cell. I picked some more low-hanging fruit. So one strategy for Grenade Guy is to always play don't use no matter what. So the don't strategy. If that happens and you're playing don't pay, then either way the payoffs are going to be 0, 0. Shown here in these green boxes. So you know this is going to be a 0, 0 payoff for both. That fills in that cell. So we've gone through just about all the easy ones. Now things get a bit trickier. So another strategy for Grenade Guy is Grenade Guy could play don't use the grenade if we're sane, but I will use it if I'm crazy. So that's modeled as don't if S, use if C. Don't if sane, use if crazy. That means that we're either going to be over here with this payoff if he's sane. If he's crazy, they're going to be over here getting these payoffs. So we got to take expected values of these two possibilities to find out what should go in our table. So let's look at your payoff first. With probability 30%, we're over here, and you're getting 0. That's going to be 0 times 0.3. However, with probability 70%, he's crazy, in which case he's going to use the grenade. In that case, you're going to get a payoff of minus 100,000. So we take expected values, minus 100,000 times probability 70%, and we get that. So that works out to 0 plus negative 70,000. Total is going to be negative 70,000. That's where this number is coming from. So now I'll do the same thing for our grenade guy. With probability 30%, he's sane, so he's going to get a payoff of 0 from this strategy. That means we look at 0 times 0.3. The other possibility is that he's crazy. That was the probability 70%. That means that we're going to be over here. In that case, his expected payoff from this strategy is going to be positive 10. So you take that payoff of positive 10, and we weight it by the probability of 0.7. 10 times 0.7 is 7, and this is just 0. So overall, grenade guy is getting 7. Now, even though grenade guy knows which one of these two nodes he's at, we're still taking expected values. That's because we're looking at the expected value of the entire strategy. Remember, a complete strategy still specifies what you do even if the nodes don't occur. So even if grenade guy knows he's sane, even if he knows for sure he's over here, he's still got a plan in case he goes crazy. And likewise, and I guess somewhat hard to believe, even crazy grenade guy has a plan for what's going to happen if he suddenly becomes sane again. So you're still playing for all possible outcomes here. So grenade guy's expected payoff is 7. That's where you put the 7 here in this table. So that fills in another one of our cells. We still have 2 more blanks. Let's see how those are going to work. So another possible strategy for grenade guy is use. That means use the grenade if you're sane, also use the grenade if you're crazy. So if you play don't pay, you're going to land at this node, this payoff rather. You're going to land at this payoff if he's sane. If he's crazy and you play don't pay and he's following this strategy, you're going to land at this payoff over here. So in your case, you're getting minus 100,000 either way. That means that your payoff is going to be negative 100,000. So that's the easy one. Now I'll go look at what is grenade guy's payoff from this strategy. So with probability 30%, he's sane. That means that the strategy yields him a payoff of negative 100,000 because sane people don't want to blow themselves up. So we weight that payoff of minus 100,000 by its probability of 30%. That means multiplying minus 100,000 by 0.3. So that's this part of the calculation. The next part is we look at what does that strategy result in if grenade guy is crazy. We said that crazy grenade guy actually prefers to use the grenade, gets some payoff from that. So in that case, grenade guy's payoff is positive 10. So we weight that payoff of 10 by the probability of 0.7. 10 times 0.7 is 7. That gets combined with the calculation we had earlier, minus 100,000 times 0.3, that works out to minus 30,000. Negative 30,000 with a positive 7 works out to minus 29,993. So that's how I can fill in this number over here in our table. Alright, we have one last cell to fill in. We have to fill in this blank over here, find out what is your expected payoff and what is Grenade Guy's expected payoff from if you don't pay, and if Grenade Guy plays this. So, let's see. If you're playing don't pay, you're going either down here or you're going down here. Depends upon if Grenade Guy is sane or crazy. Now the sane Grenade Guy is playing use if sane. That means we're going down this branch. That means we get these payoffs. Crazy Grenade Guy is playing don't use if crazy. So that means we're going down here. Payoffs are going to be shown here in green for that possibility. So if probability 70% Grenade Guy is crazy, we end up down here. With probability 30% Grenade Guy is sane, we end up at this payoff. So now I just got to take a weighted average of these two payoffs to find what should go in our table. So for you, look at the red payoffs. With probability 0.3, Grenade Guy is sane, we get minus 100,000. So minus 100,000 times 0.3. And then look at the other possibility. With probability 0.7, Grenade Guy is crazy. We end up down here, we get a payoff of 0. So 0.7 times 0 is the other case. So we do our math. 0.3 times minus 100,000 is going to be negative 30,000. This is just 0, so that works out to negative 30,000. Very last step, we'll do the same calculation for the Grenade Guy. With probably 30%, he's sane. That brings us down here. So he gets a payoff in blue, which is negative 100,000. So we do negative 100,000 times probability, 0.3. That's going to be negative 30,000 over here. Other case, he could be crazy. That gives him a payoff of 0, shown here in blue. Payoff of 0 multiplied by probability of 0.7. That's going to be 0 times 0.7. 0 times 0.7 is just 0, though. So we get negative 30,000 plus 0. That's going to be negative 30,000. So now we can complete our table and put in these payoffs in our very last cell. And now we've converted the game into simultaneous move form. So with that in place, we can now do our best response analysis and find all the Nash Equilibria. So I'll make that an exercise for you guys. Go ahead and pause the video and find all the Nash Equilibria. Alright, now let's go and check your answer. So, if you're playing pay, what is Grenade Guy's best response? Well, remember, if you play pay, the game just ends and Grenade gets $100 no matter what. So, actually, all 4 of these are best responses for Grenade Guy if you play pay. Now, if you're playing don't pay, then Grenade Guy's best response is this one over here. It's better to get 7 than to get 0 or get anything super negative like this. So Grenade Guy's best response is the don't use the grenade if you're sane, only use it if you're crazy. So that gets an underline. So now to complete the best response analysis, we'll look at what is your best response to each of Grenade Guy's 4 possible strategies. So if we're in this column over here, your best response is to play pay. You'd rather lose $100 than potentially die. So you underline 100, or sorry, I should say underline a negative 100. For this column over here, what is your best response? In that case, you'd also rather pay. Same idea, it's better to pay and lose $100 than it is to get blown up. So this is your best response. We underline the minus 100. If Grenade Guy is definitely not use the grenade no matter what, then you shouldn't pay him. So best response in this case is to play don't. Last possibility, if we're in this column over here, your best response is to pay. You'd rather get minus 100 than take a chance that he'll pull a grenade and use it. So you look at all of our underlines, we have 3 Nash Equilibria. So there's the pay, don't use if sane, use if crazy. There's pay, use the grenade. And there's lastly, pay, use the grenade if you're sane, but not if you're crazy. So that pins down all the Nash Equilibria. Now what we'll do is find the Rollback Equilibrium. Or in other words, find the subgame perfect Nash Equilibrium. So we go to the end of the game first, and then we find what is Grenade Guy going to do at his very last nodes. So the crazy Grenade Guy is going to use the grenade, right? Because they prefer dying to getting 0. They're crazy. So we put an arrow there. The sane Grenade Guy would rather stay alive, so he's going to play don't use. That also gets an arrow. So now to find the next step back in the Rollback Equilibrium, we have some uncertainty to deal with. We know that if you play don't pay, you could be either here or you could be there. You don't know. So again, you don't know if he's sane or crazy. Now if you pay him instead, you know for certain what's going to happen. If you know you pay, the game just ends and your payout is going to be minus 100. So you got to compare that payoff of minus 100 from paying with the expected payoff from not paying. So probably 30%, you're over here and getting 0. So 0 times 0.3. With probability 70%, you're over here getting minus 100,000. So you take minus 100,000 times 0.7. That works out to 0 plus negative 70,000. That's negative 70,000. So which one do you rather have? Minus 100 or minus 70,000? Well, it's a pretty easy choice. You gotta get the minus 100. So you're going to pick pay. So in our Rollback Equilibrium, you're always going to play pay over here, and the game's going to end with these nodes over here. So you have one and only one subgame perfect Nash Equilibrium. That is one and only one Rollback Equilibrium. That's going to be pay and don't use if sane, use if crazy. So once again, the Nash Equilibria and the subgame perfect Nash Equilibria are not quite the same thing. We only had one Rollback Equilibrium, but we had 3 Nash Equilibria. So it turns out that all those other Nash Equilibria rely upon non-credible threats. So let's look at one of the other Nash equilibria. So one Nash equilibrium was use. So that means grenade guy's going to use the grenade if sane and also use it if crazy. Well, that's not credible. We know that sane grenade guy prefers to not use the grenade. So any equilibrium involving use is not credible. It's not subgame perfect. What was our other non-subgame perfect Nash equilibria? That was this weird one down here. This one says grenade guy is going to, this is surprising, use the grenade if sane, but not use it if crazy. So the sane grenade guy is willing to blow himself up in this equilibrium, but the crazy grenade guy does not. That makes no sense. So that is all based on non-credible threats. We know that sane grenade guy is not actually going to use the grenade. And likewise, we know that crazy grenade guy will use the grenade, so actually both these threats here are not credible. So this Nash equilibrium is not subgame perfect. So you can rule out both of these, and you're left with just the one subgame perfect Nash equilibrium. So that wraps up our section on the grenade game. It also wraps up Chapter 6. So as you can see, rollback and Nash equilibria are not quite the same thing. If you have a Nash equilibrium that's not a rollback equilibrium, there's an issue with a non-credible threat being used. And we also got this extra insight. A lot of times in the media, people say things like, you can't assume people are rational, but in the real world they aren't. Well, actually, even things like insanity can be modeled economically. You can still be crazy and be payoff maximizing, just maximizing payoffs that don't make a lot of sense to the rest of us. So that wraps up Chapter 6. Stay safe out there with the coronavirus.